Hi. In this video, we're going to begin our discussion of the LU decomposition, one of the first of several matrix decompositions we're going to be discussing this semester, and one with very close links to the ideas of Gaussian elimination. This unit is going to be dedicated to exploring the LU decomposition. By the end of the unit, you should be able to understand what the LU decomposition is, how it relates to Gaussian elimination, and to explain that. You should be able to apply the LU decomposition to factor a matrix into a lower diagonal matrix L and an upper diagonal matrix, upper triangular matrix U. You should be able to explain how row exchanges factor into LU decomposition by leading to a form of the LU decomposition that involves a permutation matrix. You should be able to use the results of LU decomposition to solve linear systems and to be able to apply these ideas to real-world problems. In this first video, we're going to focus on an introduction on what is LU decomposition conceptually, why we're interested in it, and how we might be able to use it, and dig into each of these ideas and their derivations more deeply in accompanying videos. Okay. In the previous unit, we discussed the matrix inverse. And one of the advantages of the matrix inverse is that it in some sense stores the result of Gaussian elimination. And that lets us find solutions to new right-hand sides, but the same left-hand side of a system, easily and efficiently. In one of the challenge problems from the third unit, there was a problem looking to work out the total cost of Gaussian elimination. And for large systems, in a square system, it turns out that Gaussian elimination requires about 2/3 n cubed total steps, that is total multiplications of numbers, addition of numbers, and so on. Right? 2/3 n cubed things you need to do. This is an approximate number that only sort of applies for large matrices, but it's a starting point for thinking about this. We say that it is an order n cubed problem, meaning that if we double the size of the system, we go, say, from 2 variables to 4 variables, 10 variables to 20 variables, the cost, the amount of work we need to do increases by a factor of 8. That makes it very challenging and very expensive for big problems. On the other hand, matrix multiplication, to multiply a n by n matrix with an n by 1 vector, like we would need to do to find a solution with the matrix inverse, only requires us to do about 2n squared total arithmetic operations, additions, multiplications, and so on. It is what we call an order n squared problem. If we double the size of the problem, it only costs 4 times as much work to do that. What this means is that for large systems especially, Gaussian elimination is expensive, matrix multiplication is much cheaper. If we want to be able to solve a system for many different right-hand sides, we can save a lot of time by using the matrix inverse. We also saw how the matrix inverse provides a framework to work in symbolic matrix algebra, the idea of solving a linear system. And this can be used to gain insight and develop new approaches to problems. So these are some of the positive things about the matrix inverse, why it is such a powerful tool. But it also has some limitations. One of the biggest of these is that it does not exist for non-square matrices, and thus cannot be applied to any system that doesn't have an equal number of variables and unknowns. Even in cases where there is an equal number of variables and unknowns, the matrix inverse does not always exist for the coefficient matrix of such a system. So we can apply the matrix inverse problem, matrix inverse, to solve linear systems, but only for some linear systems. Systems of equations in more equations than unknowns can still have unique solutions, although not for all right-hand sides. Systems of equations that have fewer equations than unknowns can have solutions. They can have solutions for all possible right-hand sides in some cases. They just won't have unique solutions. And systems of any size, more equations than unknowns, fewer equations than unknowns, or equal numbers, will always have at least some right-hand sides that have a solution, perhaps not a unique one, but there is always a solution to some right-hand sides, and the matrix inverse doesn't let us deal with that more general problem. It can't help us with problems that have unique solutions for only some, but not all right-hand sides. It can't help us find a general solution if we have many solutions. And it doesn't help us figure out which right-hand sides lead to a consistent system when some do and some don't. However, all of these problems we were able to handle with Gaussian elimination. So this kind of raises a question, how useful is the matrix inverse really if there's this large class of problems that we can't handle, but Gaussian elimination still could? If we think about actually the part of Gaussian elimination that is in some sense most important for consideration of these ideas, in a lot of ways it's the forward steps that are most central to the idea of Gaussian elimination. It's forward elimination that leads to a checkpoint on the existence and uniqueness of solutions. By the end of Gaussian elimination, when we've found an echelon form, we know whether a solution will exist by looking, at least if we're working in an augmented matrix, by looking at the last column of the augmented matrix. It provides a checkpoint on uniqueness by seeing, is every variable a pivot, or are there free variables, and so on. Right? So at the end of forward elimination, we might not know the solution, but we know the type of solution. We know whether there is no solution, many solutions, or a single unique solution. Forward elimination is also the most costly part of the problem. When I earlier discussed how forward elimination is an n-cubed algorithm for a square system, in the case of a rectangular system of m equations and n unknowns, it actually turns out that it's 2/3 m squared n, square of the number of equations, and n is the number of variables. But almost all of this sort of third order cost, we have a square and an additional product, comes from the forward elimination piece. If you actually work through the cost of the back substitution piece, it's much cheaper. It only is about an m times n cost of solving the system. So just to put this in sort of framework, if we had a system of 10 variables and 10 unknowns, the forward elimination step would take more than 600 individual calculations. The back substitution step would only take 100. As we scale this to larger and larger systems, that difference becomes even more significant. So what the goal of the LU decomposition is going to be, is looking ahead about what we are going to be trying to do, is to conceptually store everything about the forward elimination steps of Gaussian elimination. It's not going to capture everything. Back substitution is much more specific. We'll only go forward with back substitution if we have a solution. And we have to deal with things differently if we have multiple solutions or a unique solution. Right? But the forward elimination steps are more robust. LU decomposition is going to aim to store that forward process. It's going to give us a similar amount of reduction of work from multiple right-hand sides as the matrix inverse. By saving the expensive part of Gaussian elimination, we can get a speed up by only needing to do back substitution for different right-hand sides. We're going to find that it's applicable to both square and non-square systems. We're going to see that it can be used to derive the unique solution if there is one, to derive the general solution when there's multiple solutions, and to determine whether a particular right-hand side leads to a consistent or inconsistent system. Right? Essentially, it will let us do everything that we can do with Gaussian elimination, but more quickly for multiple right-hand sides. Right. In our discussion forward, we're going to be using 4 different matrices, and these will come up over and over again. I'd like to highlight what each of these matrices is going to be as a preview and to help set your mind around the notation we're going to be using. I'm going to use A as a representation of our original matrix. In general, this is a coefficient matrix, not an augmented matrix. We don't apply LU decomposition to an augmented matrix because we need to be able to apply it to different right-hand sides. Right? The coefficient matrix is fixed for a given system, and so we're going to set that as A. U is going to be our representation. This is a notation we have already used for the echelon or upper triangular form of A, essentially the matrix that we found after performing only the forward elimination steps. So forward elimination takes us from A to U. We are also going to define 2 additional matrices, a matrix L, which will be a lower triangular matrix that stores much of the information about forward elimination, almost all of the information about forward elimination, and an additional matrix P that is going to be a permutation matrix, and this matrix will store any row exchanges. If we use row exchanges, they will be stored in P. All of the other steps of forward elimination will be stored in L. We are going to end up having 2 different possible forms. When row exchanges are not used, when we go through Gaussian elimination with no row exchanges, we will have a decomposition where we write A as a product of 2 matrices. Original matrix expressed as a product of a lower triangular matrix, L, and an upper triangular matrix, U. When we do need row exchanges, we are going to have to add 1 more piece to the LU decomposition, a permutation matrix that we multiply A by first. The idea behind this is that we first of all rearrange the rows of A to get it into a form where we can apply Gaussian elimination without row exchanges, and then factor that result into L and U. This is where we are going. Why do we care about this? What are the benefits of the LU decomposition? Why is it able to speed things up? Again, we're going to dig into this more deeply as we go further into the unit, but I want to give a preview of where we are moving to. The LU decomposition is one of many different matrix decompositions used in linear algebra. We will be talking about a few of them in the class. In addition to the LU decomposition, we will talk about the QR decomposition. We will talk about the eigenvalue decomposition, the singular value decomposition. all of these have the common feature that what we're doing is we're expressing a matrix as a product of matrices, like A equals L times U, where those matrices have a special form. And depending on the different compositions, the special form is different. For the LU decomposition, the form is that they are a lower triangular and an upper triangular matrix. These decompositions are helpful because the special forms of these matrices are easier to work with. They have special properties that make them easier to work with, at least for certain problems, than an arbitrary matrix filled with any values. Right? So how can we sort of get a sense of what this kind of benefit is in the context of LU decomposition? Let's imagine that we start with a linear system, AX equals B. If we are able to factor A into a product of a lower triangular and an upper triangular matrix, this becomes LUX equals B. We can take this and we can split this into two pieces. I can put parentheses around here and say, let's make a new definition. I'm going to define a vector C that is equal to UX. I'm just going to say I want UX to equal C. Then what do? We if we have this vector C, we can then substitute that in. This substitution into here gives us this form LC equals B. Now, L is a lower triangular matrix. U is an upper triangular matrix. What does this mean? The lower triangular matrix means that this system has a form that looks something like this. X1 equals B1. X1 plus X2 equals B2, and so on. Right? We can solve this system very quickly because the first line gives us an answer. That gives us an answer for X1. We can then substitute it into the next equation. That gives us an answer for X2. We can then substitute that into the next equation. That gives us an answer for B3. This is very much the same process as back substitution, except we're working from the top. We have a triangular system where we have isolated some of the variables in a hierarchical way that lets us solve the system really easily. Right? This process is sometimes called forward substitution to sort of highlight the similarities to back substitution. The most important thing is that the solution to a system like this is much easier and much faster than the solution to a general system AX. This, however, gives us what C is. If we solve this system, we get C. Once we have C, then we can solve this second system. This is an upper triangular form. This means that the last equation is something along the lines of xn equals cn, and then xn minus 1 plus xn equals cn minus 1, and so on. We have a direct answer for xn. We can substitute in for solve for xn minus 1. We can substitute and solve for the next one, and so on. Back substitution is quick for solving this system. So what we've been able to do here is split a problem that we normally would have to apply forward elimination, which is costly, followed by back substitution, which is much cheaper, into a problem where we have to do a forward substitution step, which is easy, and a backward substitution step, which is also easy, if we have the LU decomposition. Okay. That was just an introduction to what the LU decomposition is and a preview of how we're going to be able to use it to simplify the solution, to speed up the solution of linear systems, especially cases where we have multiple right-hand sides for the same left-hand side. In the next video, we are going to discuss how the LU decomposition is derived, making connections to elementary matrices. In a following video, we are going to discuss how we use the LU decomposition in solving systems. And we will also have a video going through some worked examples of to give practice on the use of the LU decomposition. Thank you, and goodbye.